Okay, so we're arriving here at MAXLab. This is the front door with the stunning keypad and the magic opening doors. It's the reception and into the main hall. So we're actually working on beam line I311, which is down here. So this is our home for the week while we're here. See some computers, drinks, keep us going. And this is a spectrum that's actually being recorded at the moment. So this is actually a titanium dioxide sample, and we can do with stopping that one now. The synchrotron itself is behind this wall here, and the synchrotron basically consists of a large steel tube which is filled with bunches of electrons, and these are accelerated around at close to the speed of light. When you move a charged particle in a circular path, it gives out radiation at a tangent, and we can use that radiation. And the beauty of that radiation compared to what we'd have in our lab source is it's tunable, so we can tune from the UV to the hard X-ray. Now I311 is optimized to work in the soft X-ray regime and the extreme ultraviolet. So in theory it should go from about 19 electron volts up to about 2000 electron volts. So that's the extreme ultraviolet soft X-ray. But in practice we only get to 40 electron volts on this particular machine. So the light comes out of the synchrotron down there at the end where you can see the yellow sign. Okay, just down there. It comes along the beam line here and into a monochromator. So this monochromator just lets us tune or choose the energy that we want to use. The light then continues up through the beam line all the way up here through some slits which allow us to adjust how much light is hitting our sample, and it also sets the resolution of our spectra, and then eventually into our chamber here. Okay, so this mass of stuff here is an ultra-high vacuum system. We use ultra-high vacuum for two reasons. Firstly, we want to keep our sample clean, so we work at very, very low pressures, ultimately 1,000 millionth of atmospheric pressure. So a lot of what we actually see on here is actually pumping. So we've got two big pumps here. We've got a pump down at the back there, you can't see. We've got a pump on the top, up there, and all that achieves this pressure. You can see on the red dial, it's 3.3 or 3.43 times 10 to the minus 10 millibar, which is, let's say, about 1,000 millionth of atmospheric pressure. The other reason we want to do that, get the pressure really low, is because electrons are very light particles, so if they collide with atoms, they get deflected. Because all that atoms also have electrons in, and you know if you put two negative charges together, they'll repel each other. So what we do is we fire the X-rays into the sample, and they will liberate electrons using the photoelectric effect, which is what Einstein won his Nobel Prize for, of course, and not relativity as everybody thinks. So we then come into our pouch, and we can set up a scan just by clicking run. Now what I want to do now is we're actually interested in what happens to our sample when we shine UV light on it. So I'll stick some UV light. You should see a bright light come on maybe up top somewhere. Okay, it's not coming on. No, it's got the hiccups. This is science and things don't work always first time. We'll try again. Okay, and our lamp has come on now, just so you can see where that's going in. This is the ultraviolet light source here, the little yellow or grey box, and it's shining ultraviolet light down into the chamber there and onto our sample. So if we go back to the hutch, we can then start a scan. So get the computer, run, and that's all there is to being a surface scientist.